I am Dr. G. Seshadri, working as Associate Professor in the Department of EEE, Institute of Aeronautical Engineering. And in the analysis of electrical network subject, today I want to discuss about the RLC parameters in AC circuits. In this, at the end of the course, the student should be able to course outcome. One, discuss the steady state response and resonance of electrical circuits to AC supply. Understand the concept of initial conditions of RLC elements to determine the transient response of first and second order electric circuits using differential equation approach and Laplace transform technique. And objective 3, illustrate the locus diagram for series and parallel circuits and describe the network functions in time and domain, frequency domain approach. And 4, to solve the relations between line and phase quantities of three-phase star and delta connected systems to analyze balanced and unbalanced circuits. And 5, to demonstrate the operation of wattmeter to measure the three-phase active and reactive power in three-phase systems. And finally, the outcome, develop the various types of active filters and understand their characteristics. Execute the digital simulation using MATLAB. So first of all, what is a resistor in a pure AC circuit? Resistor. So consider a circuit containing a pure resistor of resistance R is connected across the alternating voltage source V. The instantaneous value of this alternating voltage source V equal to Vm sin theta, and theta equal to here angular velocity to time omega t. The instantaneous value at any instant the alternating voltage is given by V equal to Vm sin theta volts. At any instant we can calculate this instantaneous value. An alternating current I is flowing in the circuit due to this due to the voltage V, and it develops a potential drop across the resistance R, which is given by VR equal to I into R. According to Kirchhoff's voltage law, the algebraic sum of all the voltages inside this closed loop is equal to 0. That means it states that the algebraic sum of potential differences in a closed loop equal to 0. So for this protective circuit, V minus the voltage drop across resistance is equal to 0. That is equal to the sum of voltage, the algebraic sum of voltage applied is equal to the sum of voltages delivered. And from the alternating equation, V equal to Vm sin omega t or Vm sin theta, and theta equal to IR. So from this, which is nothing but the voltage drop across the resistance, and from this I equal to Vm by R into sin theta. Vm bar into sin theta. So this Vm by R is nothing but the maximum value of the current. So I equal to Im sin omega t or Im sin theta. So here Im is the peak value of alternating current in the circuit or the maximum value of alternating current in the circuit. So it is clear that the applied voltage and the current are in phase with each other in a resistive circuit. It means that there is their maximum value and their minimum value simultaneously. Maximum value and minimum value simultaneously. So from the phasor diagram, you can observe that the current is in phase with the applied voltage. Or here from this waveform, you can observe that the black wave showing the voltage waveform and the red color wave is showing that current waveform. In this, the maximum value, let us say the maximum value is attained at 90 degrees or 5 by 2 radians, and when it is reaching to 180 degrees, the quantity voltage or current decreasing and reaching to 0. In negative half cycle, again it is reaching maximum, and again at 2 pi the value is going to be minimum. And next, here the voltage current relationship in a pure resistor. So resistor is nothing but a device which opposes the flow of electric current through it. So it is a pure, here we are taking a pure resistor. Now we'll go for inductor, and is also a pure inductor. So inductor. So consider a circuit containing a pure inductor of inductance L. Inductor is nothing but a coil wound, and it is connected to an alternating voltage source V, which is nothing but V equal to Vm sin omega t. The instantaneous value in this inductor is also I, value of current I, which is nothing but the current flowing through this inductor at any instant. And the alternating current flowing through the inductor induces a self-induced EMF, or the back EMF is given by EB or E equal to minus L into dI by dt. Here dI by dt is nothing but rate of change of current. The rate of change of current. Here V equal to applied voltage, which is V equal to Vm sin omega t, and when the alternating current is flowing through this inductor, here it is inducing a self-induced EMF called E, that is minus L into dI by dt, which is nothing but EMF E or epsilon. By applying a Kirchhoff's voltage law, the algebraic sum of all the induced EMFs equal to 0, or which is negative sign. Now the algebraic sum of voltages inside this closed loop is equal to 0. The sum of applied voltage is equal to sum of back EMF. And when equating these two voltages, V equal to epsilon equal to minus L di by dt, and when equating these two, V equal to epsilon, which is nothing but A equal to Vm by L into sin omega t dt, and Vm by L is again integrating both sides, will get this. After integrating this d, you will get I, and Vm by L is nothing but constant. Integrating this sin omega t dt, will get sin omega t minus pi by 2 by omega. So Vm by omega L and I equal to Im sin omega t or theta minus pi by 2. Here minus pi by 2 means the current lags the applied voltage by an angle pi by 2 radians. And here Vm by omega L, which is nothing but Im, peak current. And if we take the voltage as a reference phasor, the current I lags in a pure inductor by 90 degrees. Here in this waveform, the current and voltage relationship, we can observe that here the applied voltage V, which is nothing but a sine wave, and the current also nothing but a same sine wave, but it lags the applied voltage by pi by 2. So this is voltage waveform, this is current waveform. It is clear that the current lagging the applied voltage by pi by 2 radians in a pure inductive circuit. So the minus sign minus omega minus pi by 2. Next, inductive reactance. So this inductive reactance is nothing but the resistance or reactance offered by the inductive circuit. So which is nothing but it is also opposing the flow of current. It is nothing but it is also opposing the flow of current, called inductive reactance. So inductive reactance is equal to offered by Im is nothing but omega L. XL is nothing but omega L and omega equal to 2 pi f. So the inductive reactance varies directly as the frequency. If the frequency increases, the inductive reactance also increases. For inductive circuits, XL is the inductive reactance. And then AC circuit containing a pure capacitor. When a pure capacitor is connected across an alternating circuit, alternating voltage source, then the instantaneous value of this voltage is same, which is nothing but V equal to Vm sin theta. Vm sin theta. Here, if Q be the instantaneous charge on the capacitor, Voltage is nothing but, let Q be the instant charge on the capacitor. The EMF across the capacitor this instant is Q by C. And according to Kirchhoff's voltage law or Kirchhoff's loop rule, the voltage, applied voltage is equal to the voltage across the capacitor, or the EMF across the capacitor at any instant. And by the definition of current, we know I equal to rate of change of charge. So I equal to dq by dt. Here Q, Q equal to CV, but V is Q equal to CV, but V equal to Vm sin omega t. And substitute this in the expression current, I equal to d by dt of C Vm sin omega t. So SC is constant and Vm is constant, and d by dt of sin omega t is nothing but cos omega t into omega, and I equal to C Vm omega cos omega t, or I equal to V by 1 by omega c into sin omega t plus pi by 2. Here omega t plus pi by 2 means that the current leads the applied voltage by, here V is taken as reference and the current is leads the applied voltage by 90 degrees. In a pure capacitor, the current leads the applied voltage. The instantaneous value of current now is nothing but I equal to Im into sin omega t plus pi by 2. Where Im is nothing but Vm by 1 by omega c, Xc. So Xc equal to Xc is the capacitive reactance. So it is clear that the current leads the applied voltage by pi by 2 radians. Here. Current leads the applied voltage by pi by 2 radians in a capacitive circuit. A capacitive reactance, the peak value of current in this capacitance circuit is Im, and Im equal to Vm by 1 by omega c, which is nothing but Vm by Xc, but Xc equal to 1 by omega c and 1 by 2 pi fc. Here the capacitive reactance is inversely proportional to the frequency. If the value of frequency increases, the capacitive reactance value decreases. And all this resistance is measured in ohms, which is also the property of resistor is the opposing the electric current through a resistive circuit. In a resistive circuit is nothing but resistance. And in capacitor, the capacitive reactance is measured in ohms. On inductor, the inductive reactance is also measured in ohms. Here in this RLC parameters, resistor, the energy dissipated in the form of heat. In resistor, the energy dissipated in the form of heat. And in inductor, the energy stored in the form of electromagnetic field. And in capacitor, the energy stored in the form of electric field or electrostatic field. There are different types of resistors. In a conductive material, the property of resistor can be calculated by using the formula R equal to rho L by A, where rho is the resistivity in ohm meter and L is the length of the conductor and A is the cross-section area of the conductor. If the cross-section area of the conductor increases, the resistivity value decreases. And in pure resistor, both the voltage and currents are in same phase. If the length of the conductor increases, the resistivity value also increases, resistance value also increases. When the current flowing through this resistance, the energy is dissipated in the form of heat. So resistance is energy dissipating element, energy dissipating element. And in inductor, when the alternating current flows through the inductor, then EMF is induced, and also the energy is stored in the form of electromagnetic field, in the form of electromagnetic field. And in capacitor, it is charged. When the alternating current flows, it is charged, and also the energy is stored in the form of electrostatic field, electrostatic field. So in a resistor, the resistance offered by the resistive circuit is in ohms. In inductive circuit, the inductance offered by the inductor is inductive reactance, which is also measured in ohms, which is nothing but XL equal to 2πfL. It is directly proportional to the frequency. And in capacitor, the capacitive reactance offered by the capacitance is measured in ohms, which is nothing but 1 by omega c, which is nothing but 1 by 2 pi. If the voltage is applied or V or E applied across a resistive circuit, alternating current, the current will flow through this, and because of this resistance there is a drop called voltage drop. We can calculate the current, the instantaneous current, as I equal to Im sin omega t. And an inductor is connected across, a pure inductor is connected across a voltage drop, voltage source V or E. The current, instantaneous current, can be calculated as I equal to Im sin omega t minus pi by 2. And a capacitor, a pure capacitor is connected. Here also the voltage rule can be applied. So here the current is I equal to Im sin omega t plus pi by 2. Minus stands for lagging, plus stands for leading. We can connect this both resistor and inductor in series circuit. In series is called RL series circuit. When we connect a resistor in series with an inductor is called RL series circuit. And we can observe the behavior of this RL circuit. And we can connect a resistant, inductor and capacitor in series is called RLC series circuit. When we connect a resistance in parallel with an inductor is called RL parallel circuit. When we connect resistance, inductance and capacitance in parallel is called RLC parallel circuit. We can analyze the behavior of these RL series circuits and RLC series circuits and how the circuit behaves, like is it inductive circuit, inductively, or a capacitive circuit. We can study the behavior of these RLC circuits by connecting. So today I have discussed about the RLC parameters and the behavior of these RLC components when connected to an AC supply. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.